So we might reasonably ask, well, what happens to the limit of as x approaches infinity of a polynomial over a polynomial? Wouldn't substituting infinity into this expression give us infinity over infinity by direct substitution? Well, yes, by direct substitution, of course, we see that. I'll write this out. By direct substitution, if we could do such a thing, by our first rule, that is the limit as x approaches infinity of x to the n, we get infinity, so we would get infinity over infinity. Well, this is what we call an indeterminate form. It's just like 0 over 0. It's meaningless from the perspective of finding a specific value. And yet we know that this will have a behavior. This function will approach something, but the question is what? So here's the method. What we're going to do is that we're going to divide the numerator and denominator. Numerator and denominator by x squared, or by x to the highest power in the denominator. So maybe I should make this a more general rule right here. It's not always x squared. It could be whatever the power is in the denominator. By x to the highest power in the denominator. And let me show you how this rule is going to work. Okay. There is a rule that says that if you have a fraction, of course, you multiply the numerator and the denominator of that fraction by the same value, equivalent to multiplying the fraction by 1, which doesn't change it. So if I have 3x plus 1 in the numerator, and I have x squared plus 2x, so that should be minus 2x. Watch what I'm doing here. Minus 2x plus 2. The rule here says, okay, divide the numerator and denominator by x to the highest power in the denominator. Well, that's x squared, so I'm going to multiply by 1 over x squared in the denominator and multiply by 1 over x squared in the numerator, which seems like an awfully funny thing to do until you actually carry out that multiplication. We're going to distribute. So we're going to take the limit as x approaches infinity of 3x times 1 over x squared, which we know is going to be 3 over x, plus 1 times 1 over x squared, which is going to become 1 over x squared. And then x squared times 1 over x squared just becomes 1, minus 2x times 1 over x squared, that becomes 2 over x, plus 2 times 1 over x squared, and that becomes 2 over x squared. And you see what's happening. We're just distributing this factor into each of these terms. And the reason why we want to do that is that now we can use our rule from before that tells us that if we have 1 over or some constant over x to a power, as x goes to infinity, that term goes to 0. So look at what we've got right here. We've got 3 over x. 3 over x as x goes to infinity goes to 0. And 1 over x squared as x goes to infinity goes to 0. As x goes to infinity, 1, well, that just stays 1, minus 2 over x as x goes to infinity goes to 0, plus 2 over x squared, that goes to 0 too, right? So we're evaluating each term in the numerator and denominator, and that gives us 0 divided by 1, which is not undefined, it's equal to 0. And that's our limit in this case. All right, let's try it again. This time, let's try it with our limit as x goes to negative infinity of 4x squared divided by 1 minus 8x squared. And again, we use our rule right here. It says that, well, we're going to divide the numerator and denominator by x to the highest power in the denominator. So this is going to be the same as taking the limit as x goes to negative infinity of 4x squared over 1 minus 8x squared to the 1 times 1 over x squared by each term in the numerator and denominator. So we're going to rewrite our fraction this way. We're going to rewrite our fraction as the limit as x goes towards negative infinity of 4x squared times 1 over x squared, well that's just 4, divided by 1 times 1 over x squared, that's 1 over x squared, minus 8x squared times 1 over x squared, and that just becomes 8. Well, this limit is going to become 4 divided by 0 minus 8, and we know that that reduces to be negative 1/2, and that's our limit in this case. Now, this may look familiar to you if you recognize these as rational functions. And back when we were dealing with rational functions in algebra, you may recognize the fact that if I had a function like 4x squared divided by 1 minus 8x squared, it would be the kind of function that has a vertical asymptote. A horizontal asymptote. We're not worried about vertical asymptotes. We know vertical asymptotes occur wherever the denominator is 0, but would have a horizontal asymptote at y equals negative 1/2, and that was due to the rule that told us that if we had a numerator and denominator that had the same power, that had the same exponent, then we would just simply take the leading coefficient divided by the leading coefficient to get that value. Well, this is confirmation of that fact. Just like in our first case, we had 3x plus 1 over x squared minus 2x plus 2. The degree of the numerator was less than the degree of the denominator, and that indicated that the vertical asymptote, the horizontal asymptote, would be the line y equals 0. So we've actually just gone through and used a limit to confirm those facts about horizontal asymptotes, and we'll have a chance to use that later.